Hello everyone, let me introduce our work using pre-trained language model to resolve textual and semantic merge conflict. This is the joint work with my advisor Isita and Todd Mike Shiven from Microsoft. Let's get started. Nowadays, merge conflict is very common. For example, here, variant A and B starting from the same base O. What they did is that basically they touched the same region of the code with different content. For example, here, in variant A, it says include A.h. In variant B, in the same area, it says include B.h. So basically, if you want to use the git merging algorithm to produce the merge code, it can be done. So usually, you need to invoke the developers in the variant A and B to come up with solutions that decide which part of these changes will be appeared in the final merged code. So it's called a manual fix. So let me show you some fun facts of merge conflict. From the existing study, it shows that nearly 20% of the merging attempt could be finally a merge conflict. And a single merge conflict can even delay the whole development process from hours to even days. And sometimes merge mania may happen, which means that developers actually spend more time resolving the conflicts rather than developing the features. It's a disaster, isn't it? So here comes our motivation. So rather than invoking developers to manually fix these conflicts, could we actually use some tool support to automatically resolve them? That's our motivation. And that's the question that we're going to ask and answer in this paper. So let me show you a semantics merge conflict in divergent fork. So divergent fork is a structure that's used in Microsoft Edge. Basically, there exists two basic and major repository here. So the branches here. The first one is called upstream, and it's also called Chromium. Is maintained by the open source developer. The second one is called the downstream. It's basically Microsoft Edge. So what does the divergent fork means here is that in the downstream, it only periodically pull from the upstream, but very seldom merge back. So for example, here, the function foo was first initialized in the upstream, and then it was forked in the downstream. And as the time goes by in the upstream, so those two branches are developing individually, and the function foo was renamed to the bar in the upstream. And then at the same time, in the downstream, the function foo, they found, okay, it's interesting. So we're going to use another function useful that called the function foo here in the downstream. And when they try to merge this code, this is going to happen. So basically, the merged code could be produced, okay, because there is no textual merge conflict. However, if you want to run the code, you will find there is a compiler error here. So basically, it cannot find a function definition for foo here. So to come up with a fix is very straightforward if you look at this picture. So for example, just by changing every call sign of function foo to bar. But in the real world, if you are a Microsoft Edge developer, what you're going to do is that you're going to start from the merge conflict all the way down, go back in the downstream. And then you will find, okay, there's no reason why this is a merge conflict. Basically, it's not your fault. And then the only choice you left is basically to dive into the upstream, which you are not the most familiar. And then you will find out, okay, after the inspection, maybe hundreds of commits, you'll find, okay, the function foo will somehow remain the bar. And then apply the similar changes to the downstream will generate a resolution for the merge conflict. So the previous example was not artificially contrived. It's actually happening in day-to-day Edge development. For example, and this is the case that the compiler complains about. It cannot find the definition for the function is canonical in your downstream. And then the root cause of this would exactly look like the foo and bar example. Is basically the upstream is canonical was renamed to canonical, and then apply the similar changes to the downstream to fix this. So there were 800 commits in the 3 months range were just introduced to solve merge conflict only, and each one of them, because it will require the expert to inspect the commits in the upstream, so it's quite expensive for them to solve. But compared with this very expensive human labor, what is more scalable? The answer is GPT-3, the large language model. So by the time that we wrote our paper, so GPT-3 was the largest language model, and then it has been seen very successful in many traditional NLP tasks, for example, like question answering, to the more recently code generation. So basically, what we're going to do here is that we're going to formulate the merge conflict problems into the prompt and then feed the prompt to the model to help for the model to give us a resolution. So to understand how this works, we first need to understand how GPT-3 works. So this is an example in GPT-3 using one-shot learning. For example, here, what we're gonna put in the prompt is actually the input to the GPT-3. It's described in plain text, and then the output is what GPT-3 returned to us. So in the prompt, there exist two parts. The first part is called shot. So basically, in shot is an example about a question answer pair, and right after that is a test derivative. It's basically a question. So for example, shot we ask, what's the answer for the question apple is red? So basically, you build an analogy with the short and the task derivative. For example, apple to red is equivalent to what? So GPT-3 was able to build this analogy and output purple to. And in addition to one-shot learning, another learning in GPT-3 is called zero-shot learning. So basically, you can just directly ask the model with the task derivative without feeding any shots, without feeding any example. So you can just directly ask, what's the capital of Spain? So the model will be able to produce the memory for you. And the reason why the model is able to produce such an answer is because the GPT-3 model has the highest probability that this method is coexistent with the prompt, with this what's the capital of Spain in its training set. So let's see the overview of our tool Gmerge. So Gmerge contains basically two parts. The first part is called data curation. Basically, it collects all the conflict-related changes from the repository, from the commits, and then to form the conflict description here. And then from the conflict description, we're gonna move on to our second module called prompt engineering to basically create a new prompt that is most effective for the GPT-3 model to return to an answer for us. So just inspired by this one-shot example, this is what we're gonna do here in resolving semantics merge conflicts. Basically, in the short part, we're gonna provide how historically merge conflict was resolved. And then in task derivative, we're gonna put the current conflict and then the current changes related to the conflict. And then we will ask the model, what's the resolution for this? Let me give a concrete example about this. For example, here in the shot, so because this is an experience paper that we're gonna show you some experience in our shot design. So basically what we're gonna do here is that we're gonna manually select this shot for all experiments in the semantics merge conflict. The reason why we're gonna do this is because this shot, we want to, by feeding this shot to the model, we want to save as much token space as we can for the later, like a task derivative, because that's the meat of the work. And what is the short means here is basically to guide the GPT-3 model what's the ideal output. So basically, what's the content in short has no relation to the actual merge conflict that we're going to come up with a resolution on. So that's the reason, because the input size of the GPT-3 model is so limited, we're gonna save the space for the later task derivative part. So from this part, we're gonna first starting from this error messages we get, because that's the only source that we know, okay, this is a merge conflict, and that's the only information we can get. So from this error message, what we do the first is that we're gonna extract this chemical as the keyword. And starting from the keyword, we're gonna select every pairs, like related to this function is chemical changes in the upstream, and then we collected all its changes together, and then we use some customized heuristics to prioritize some kind of changes like to the others. And then after that, we're gonna feed this line that contains this merge conflict that the compiler basically complains of, and then requires the model to come up with a fix. For example, this is actually the fix generated by the model, which is the exact fix provided by the developer. So in our evaluation, we're going to ask three questions. The first one is that what's the accuracy of our model? The second one is that the different kind of prompt engineering strategy positively affected accuracy. The third question is that basically is the size of the model actually affected the result or not? So here we have collected more than 300 actual real-world Microsoft had semantics merge conflict in 8 months of period of range. And then we have three different baselines. The first one is called the GPTJ. Basically, it's very similar to GPT-3, however, with less parameters. And the second one is called string merge, which is the closest way we get to the static analysis baseline, and basically mimics how every day, like Microsoft Edge developers use the string pattern analysis to manually fix such a merge conflict. And finally, we have our transformation.tasks in this baseline, which is the SODA program synthesis approaches, which is designed for string transformation. And then from the table we provided here, And then we can see that the accuracy of the GPT-3 actually outperformed the rest of baseline by a large margin. And in this part, we're going to show that how different prompt engineering designs affect the result. For example, we can see that just by having a very simple shot as the input to the GPT-3 model actually significantly improved the result. And also we found that feeding more context to the model actually helped to increase the result. And then with the heuristic that we prioritize some kind of changes, pops up in just appears that before the others actually improve the results. So if you are interested in heuristic, please refer to the paper. So finally, we're going to ask a question about whether the size of the language model matters. So because the language model is kind of like a probabilistic model every time, it will return the different results for you if you query many times. So it's possible that they will return different answers. So that's the way we're going to do the experiment. We're going to repeatedly query the model. So if the resolution was found in any trials, and then we will just mark a confident result. So for example, from this picture, we can see that large language model has a better accuracies on both single model trials and in multiple model trials. And if the model size is larger, and it's more likely to produce extra merge confidence resolution, for example, given 10 trials, than the smaller size of language model. So finally, we would like to understand whether this 2G merge can be generalized to some textual merge conflict, which are presented at the beginning of our talk. So basically, we adopt the same data set used in the state of our research, which contains 120 header files, conflicts, and 38 Markov conflicts in Microsoft Edge. And for example, the example here is basically means that if there is this duplicated header files, we can just keep one of them in the final conflict region. And because in this case, we don't have the access to do the data curation anymore. So what we're going to have is just the conflict descriptions from the dataset. So it brings us a unique opportunity to just test whether using the prompt engineering alone will produce a great result. So here's the case, because we cannot tune the task derivative, we cannot change it anymore. So what we're going to do is that we're going to feed this model with different shot selection strategies. So in this case, we have two different shot selection strategies. The first one is called random shots, which is adopted from the existing work. For example, if we use the changes from A or B in this order, or flip the order from B first and then A second, or we just dump one of the result, or dump one of the changes and only adopt the others. So in this case, we have the random shots. And then the second one, that in the shot selection strategies, we're going to choose the shots using our own domain-specific knowledge. And from this example, what we're going to see here is that using the prompt engineering by using the representative shots actually improves the results. But what is more interesting is that we have seen that our model actually performed better than SOTA model in the Markov dataset. But however, in terms of the header file dataset, our model didn't perform as good as this data file work. We would like to understand why this is the case. So we dive into the detail, and we found that this is one of the examples which shows the limitation of our tool. For example, here is that the logging.h is basically one header file that Microsoft Edge didn't use. So basically, if this is happening in conflict region, it should be always removed. So this kind of a domain-specific knowledge we cannot just learn by using the GPT-3 model. GPT-3 didn't have this prior knowledge. So in this case, the reason why the existing work can solve this is because they invested to design some domain-specific languages to basically extract these rules for the specific cases. So basically, another experience we learned from this work is that using language models still do not alleviate the need for designing some domain-specific language or using some of this domain-specific knowledges for this problem. And finally, we have our conclusion. In this work, we present data-driven 2G merge, which use the causal learning to resolve merge conflicts. And we have evaluated our tool on both textual and semantic conflicts problems in Microsoft Edge. So we obtained state-of-art performance on the semantics merge conflict resolutions and modest and respective performance on the textual merge conflict resolutions.